session today. I will be talking today about the North American separator manufacturing and expansion, as mentioned. So especially how our Celgard separators can enhance lifespan in those type of cells. So first of all, I would like to begin by briefly introducing Celgard, our parent company, and highlighting also our presence here in North America. And then from there on, we will move into requirements for battery energy storage systems, or better to say this energy storage cells, and how they differ from cells being used in electric drive vehicles. Further, I will walk you also through our Celgard product portfolio, and we will finally dive a little deeper into a few technical highlights of our solutions, and specifically how they can really help to extend the lifespan of energy storage systems and also make large cell assembly processes more efficient. With that, so Celgard became part of Celgard in 2015. And so today we belong to this really large, diversified chemical company that is headquartered in Tokyo, Japan. Celgard has a long history, and it was founded over a century ago. Today, we employ more than 50,000 people worldwide. In the last fiscal year, the company generated a net sales about $20 billion, and roughly 45% of that is in the materials segment. Within the materials segment, there's a major division for environmental solutions, and that's also where separators, like the ones we are discussing today, play a key central role. So how do we fit really into today's session, you may ask? As the population grows and more countries transition toward low carbon economy, the energy release and also energy storage systems become more important. So this creates a clear demand for advanced solutions that can both support large-scale energy storage system, also ensure performance and long-term sustainability. Our separators, Hypor as well as Celgard, are the reliable choice that can address this need by enhancing the safety, improve durability, and also enable more efficient cell assembly. So together with that, we extend the cycle lifetime and the reliability of ESS application systems. So just in case for everybody who does not know, separators are part of the actual cell, so they're sitting right between the cathode and the anode, and they provide electrical insulation between the electrodes, so we are not micro-shorting the system, but also ionic conductivity for the lithium ions, and can also improve safety, and the separators also serve as electrolyte reservoir. So Celgard is perfectly positioned here in North America, right in the heart of what we call the North American battery belt. So we are your local domestic partner for offering both wet and dry separator solutions, and also solutions for the lead acid batteries. Another important point is that also differentiates us from other suppliers here in North America is that we are neither a prohibited foreign entity nor a foreign entity of concern. So our battery separators are fully compliant with the One Big Beautiful Bill Act. Beyond compliance, we already operate established manufacturing facilities that are ISO 9001 and also IATF 16949 certified. Building on this strong foundation of history and expertise, we are expanding further in the North American market. And in fact, our new Hypor wet process polyethylene operations is coming online mid of 2026. So I have already mentioned Hypor and Celgard a couple of times. So let me explain a little bit more in detail what's behind that. Hypor represents our wet process polyethylene lithium-ion battery separators. And Celgard stands for our dry process polypropylene lithium-ion battery separator. Each of those product lines has a unique attributes and also play a distinct role in lithium-ion batteries and specifically in ESS applications. So Hypor, being the polyethylene-based separator, can achieve lower thicknesses, offers a low temperature thermal shutdown, and also thanks to the biaxially stretching process, offers high mechanical strength. Celgard, on the other hand, is polypropylene-based, and the dry process makes it highly cost-effective. The uniaxially stretching also creates a unique pore structure that provides high compression resistance. and the polypropylene itself gives it excellent dimensional stability. So with both of these technologies, we fit into all type of markets, and we serve also the full range of markets, from consumer electronics over electric drive vehicles, from HEVs over PHEVs to full BEVs, as well as all types of energy storage systems. So at Celgard, we are building on more than 50 years of experience and know-how, since we pioneered the dry process, but also we pioneered the Trilayers and were the original inventor of ceramic coatings. Our first plant was built in the 1980s and is located in Charlotte, North Carolina. This plant also serves as our headquarters today. Over the years, we expanded this facility several times, but also added a new site in Concord in 2011. The Concord plant is equipped to serve really the mass market production of separators for both energy storage and also electric drive vehicles. And looking ahead, as I mentioned, we are also further expanding our Charlotte facilities to integrate the high power wet process coating lines. Here you can see a little bit more, a few more details on the Charlotte expansion for high power. Alongside the coating lines, we are also adding slitting and packaging, with commercial operations scheduled to start in mid-2026. But also, as you may have seen in the news, we are not quite stopping there. We are bringing the entire value chain of polyethylene-based separators to North America, from the base film through the coating, slitting, and manufacture and finishing. That full process plant is now under construction in Port Colborne, Ontario, in Canada. It's really close to the Niagara Falls. And the groundbreaking ceremony was held in November of last year, and it's on track to begin commercial production in 2027. This expansion represents roughly a $1.5 billion investment with the capacity to produce 700 million square meters of finished coated film. With these two expansions, our strong presence in both wet and dry technologies, we are fully committed to serving the North American market for the long term. If we look now at the demand for battery energy storage systems over the coming years, it's clear that lithium-ion will still continue to dominate the market. As of Q2 2025, approximately 67 gigawatt hours of battery energy storage solutions are already operational worldwide. This marks a 33% increase compared to the same time last year. So looking ahead, forecasts suggest that the market could reach as much as 900 gigawatt hour for lithium-ion alone. That being said, we are not limiting ourselves to one chemistries, and we have a really broad portfolio of membranes that support not only lithium-ion, but also lead-acid flow batteries and other technologies. So with this, we are committed to really grow alongside the expanding energy storage market. So yeah, as mentioned, we have a wide portfolio of separators already today serving lead acid, lithium ion, sodium ion, and next generation technologies. But our portfolio also includes technologies for flow batteries, aqueous batteries, and supercapacities, and even membranes for battery vents. Beyond separators, we are also providing engineering plastics for battery casings, frame plates, housings. These type of materials are based usually on modified polyphenylene ether or polyamide resins. And they can be glass fiber reinforced or enhanced with flame retardants to provide high mechanical strength, dimensional stability, and also improved fire safety. Furthermore, Asahi has a micro device business unit that provides coreless current sensors for precise fast current detection for efficient inverter and DC-DC operation. So besides being fast and accurate current control that enhances the grid stability, these type of sensors also are low in heat generation and reduce therefore container cooling needs and can improve the system reliability. So when we look at what energy storage system manufacturers prioritize today, there's a few things that clearly stand out. First of all, cost, safety, and cycle life. So this remains still to be the key selection factor for any type of grid scale customer. But second of all, there's also capital expenditures and long-term revenue potential. These are both critical for evaluating the return of investment and also the overall viability of large projects. The Volta Foundation's 2024 battery report also emphasized how bankability, basically in other words, how utility scale projects, whether utility scale projects can be financed or not, is also tied directly to factors like degradation, cycle life, and also product warranties and guarantees. So while lead acid and lithium ion technology is already established nowadays, we are also seeing emerging technologies that gain more and more traction, especially in niches that call for longer durations. For example, flow batteries and metal air are starting to be deployed, but also where enhanced safety is needed, sodium ion and aqueous systems are of interest. And for reduced reliance on critical raw materials, it is expected that all of this additional storage solutions will grow in the market within the next years. Here's a short overview about the key differences between energy storage cells and also EDV cells. The primary need remains to be cost for both of them, but partially more for ESS since the cell capacities become larger and larger. There are now announcements of energy storage cells with over 600 ampere hours and even up to 1,175 ampere hours of capacity per single cell. And with that, this impacts significantly also the manufacturing yields and cost more dramatically than for EDV cells. In terms of long cycle life, most ESS applications require a cycle life of about 6,000 to over 10,000 full cycles, while normal EDV cells only require about 1,000 to 2,000 full cycles with only partial depths of discharge. The energy density of ESS cells is usually moderate because nowadays a lot of systems actually use LFP. But the power density is also mostly moderate. As you can see in this graph where we plotted the cycle life versus the power. All the energy storage systems are kind of falling onto the low power side, with one exception being UPS. Because in the UPS systems, you require you have to be able to deliver high power in short amount of times. But driving any type of electrical vehicle, you will know that the power demand is much more dynamic since we are accelerating regularly and also have regenerative braking. So in this talk, I specifically focus on enhanced durability and cycle life, since these are the key degradation profiles for energy storage cells, and where in EDV cells also temperature and power stress is more significant. So let me discuss with you what type of solutions we offer at Celgard. At Celgard, we have a variety of thickness ranges between 25 micrometer down to 9 micrometer for the base film. Our wet polyethylene processed wet processed hyper separators from our sister company can go as thin as 4 microns today. In the energy storage space, most of the cells utilize separators that are somewhere between 20 micron to down to 7 micron today. We offer also everything from mono-PP for high power durability, like for UPS systems, to multi-layers for enhanced safety. We can maintain excellent control over pore size to match specific application needs, and we also offer a wide range of coating options. So anything from a ceramic alumina coating over different type of adhesive coatings. And in my next slides, I will be also highlighting our newest generation of coatings, the so-called cool stack adhesive coating, that can help you to decrease CapEx and OpEx while increasing yields in manufacturing. So even though I briefly mentioned that Celgard has actually pioneered the ceramic coatings as the inventor with our original 568 patent, PP enables us to also use base film only. This is due to the, especially in ESS applications, where a lot of systems use LFP cathodes, but this is mainly due to the high oxidation stability of polypropylene in electrochemical systems. So this is important since ESS cells operate over decades and reliability is key, but also enabling the usage of base films without a ceramic coating enables more cost-efficient cell designs. So here you see a floating charge test that we performed at 45 degrees C, where we apply a constant voltage of 4.2, 4.35, or 4.5 volt. And we let the voltage float for 25 days at this temperature. After the cell tear down, we observe that the pore structure is unaffected, and we do not see any reduction in film thickness, nor any decline in mechanical strength, which means also that there's no pore closure or pore collapse, and the cell remains its initial resistance. With that, our Celgard separators provide high durability at high voltages. But as mentioned, ceramic coatings are often a solution to increase safety. And on the other hand, I also just mentioned that we can reduce cost by going to only a PP solution. So let's talk about Trilayers for a moment, because Trilayers are our solution for cost-efficient safety in energy storage systems. Celgard Trilayers consist of polypropylene outer layers and a polyethylene middle layer. Since the polyethylene has a significantly lower melting point, namely at around 130 to about 135 degrees C, versus 160 degrees C for polypropylene, the polyethylene layer actually acts as a thermal fuse, so provides low temperature shutdown. So during any safety incident, the pores are closing and the current is being cut off. So with that, Celgard has been used for many years, or Trilayers and specifically has been used for many years and continue to be used by leading ESS cell manufacturers worldwide. Oops. Trilayer separators provide, however, additional benefits besides safety, also by mitigating metal contamination. Their layered pore structure also improves the electrolyte distribution and helps maintain a uniform ion flow, which minimizes, on the other hand, localized current densities. This reduces the risk of lithium plating, dendrite formation, and microshorts that can normally cause self-discharge, ultimately enhancing both cycle life and also safety. We estimate that utilizing Trilayers in newer cell design can actually improve manufacturing yield by about 1%, which represents roughly $1 million in cost savings per gigawatt hour of production. Our separators are also highly resistant to compression from electrode expansion or also internal pressure increased over cycle life. On the left-hand side, you can see the DCIR versus different types of C rates, and we plotted the control separator for the control and for also the Celgard in the solid line, and the compressed separator at 10 megapascal in the dashed in the S-dashed line. As you can see, the Celgard separators don't experience any significant increase of DCIR, while the control separator increases in DCIR over all C rates. This is rooted in our unique lamellar pore structure with this type of polypropylene pillars in between. This polypropylene pillars serve as these polypropylene pillars are similar to a spring in their function. So they help to preserve the structural integrity even under stress. This compression resistance helps maintain pore structure and ionic pathways under high stack pressure, and which also directly supports higher capacity retention over time compared to the conventional separators, which is especially important in very large prismatic hard case energy storage grid cells, while also maintaining, on the other hand, for example, fast discharging rates in UPS systems, even under compression. Let's talk about electrolyte wettability for a minute. The hydrophobic nature of polyolefins, this is true for polypropylene and polyethylene, can be challenging for wettability at times. This is even more true since cell designers are moving or continue to push the boundaries to larger and larger formats, like the 4680 cells, but also the 600 ampere-hour plus prismatic cells. Electrolyte retention and absorption becomes really critical in this type of large cells. There's also several publications now on how electrolyte motion due to electrode expansion can lead to decreased cycle life. There's publications by Jeff Dahn, but also some publications by BMW, also on the concentration gradient that it creates in the electrolyte. Part of the challenge here is also the reabsorption of the electrolyte into the pore structure of the separator. And here at Celgard, we have a new technology for that is called DuraWet, that can increase the cycle life and also the low temperature behavior, since the base film is inherently retaining the electrolyte. DuraWet can also reduce, therefore, overall filling times and also reduce soaking times, and therefore improve yields, so as you are not running into copper dissolution, especially if you're not using a pre-charging step. In this schematic, I want to illustrate the poor retention of any type of polyolefin membrane with the electrolyte. While usually a lot of cell designers typically look for the resolutions such as ceramic coating, the ceramic coating only really helps to spread the electrolyte in plane, but it doesn't soak up the electrolyte into the pore structure. Our new DuraWet technology provides electrolyte retention due to higher affinity to the electrolyte down to the deepest of the pore structure. Let me show you a video here. This video shows is demonstrating a bit the effect. It shows two types of DuraWet separators and two control separators. In a ventilated fume hood, we immerse the separators in a petri dish with electrolyte, and we pull the separators out, so there's no vacuum bite, so nothing that can force the electrolyte to go into the pore structure. So by that, you can see that the control separators are actually repelling the electrolyte pretty fast after a few seconds, while the DuraWet separators are really continue to be soaked into electrolyte. And this keeps up for several minutes in a ventilated fume hood until eventually the ventilation will also will evaporate the solvent. So with this improved electrolyte retention and absorption, we can actually decrease the electrical resistance by up to 30% and keep the electrical resistance low over cycle life. So this helps to improve the cell performance, the cycle life, but also the safety. As mentioned, we also see this advantage of increased electrolyte retention at low temperatures. So here you see some cycle data of DuraWet versus a control at -10 degrees C. Since the viscosity of the electrolyte is increasing at low temperatures, the electrolyte starts to be pushed out of the pore structure slowly. And this you can see by the control dropping in capacity. Our DuraWet separator maintains a 10% higher capacity retention at here 250 cycles in these examples. So DuraWet is really your solution for dependable operation across a wide range of temperatures. Performance, however, is not only a challenge when it comes to is not the only challenge when it comes to large prismatic cells, as they are also commonly used in grid applications, but also the cell manufacturing itself. Nowadays, the majority of large prismatic cells actually use adhesive-coated separators to increase productivity and yields. Our newest adhesive coating technology, what we call CoolStack, allows for high-speed and low energy consumption stacking and heat press. But with the twist that we are actually not needing to heat press, but also can press the separator without applying any heat. So how does CoolStack enable such a good adhesion at low temperatures? Here you can see like a schematic structure of our separator. The non-continuous coating creates anchor points with the electrodes to stay in place while preserving porosity, air permeability, and also the ion transport. The adhesive layer is usually about 2 micrometers thick per side, but once you heat press or once you press the separator, it's largely absorbed by the electrodes. We can also combine our CoolStack adhesive coatings with ceramic coatings, which range typically somewhere between 1 and 3 micrometers, depending on your requirements. Our CoolStack separator, as mentioned, can be pressed at room temperature for as little as 3 to 10 seconds. This is vastly different from state-of-the-art adhesive separators that needs to be usually activated at 70 to 90 degrees C, and also require press times of about 90 seconds for really large and thick stacks. With this type of reduced press times, CoolStack actually enables a higher throughput in your facility, but also decreases the capex since no preheating is required any longer, and even taping can be potentially eliminated. Further, also OPEX will be decreased due to the lower energy consumption, not only of the press alone, but also the lower energy consumptions of your dry room HVAC. Minimizing stack misalignments, taping, and unnecessary moving around of your stacks can actually also lead to increased yields. So we estimate that in total, your overall savings may amount up to $21 per square meter of separators by using our CoolStack technology. A lesser known and lesser discussed contributor to long cycle life is actually how we control swelling in polymer membranes. Swelling is a natural occurrence in all type of polyolefin separators when the film is absorbing the electrolyte and expanding, volumetrically in terms of thickness, but also dimensionally in terms of width and length expansion. This behavior is mainly influenced by the polymer structure and the porosity of the film. Solvent-polymer interaction cause chain relaxations and also therefore dimensional change. So you may wonder, like, why does that matter? Usually, a slight swelling is actually a good sign since it indicates that the electrolyte is absorbed by the separator and also hence lowers impedance and improves ionic conductivity. However, on the other hand, excessive swelling increases the stack pressure and also causes deformation and wrinkles. This can lead to pore deformation and even pore collapse and uneven ion transport, resulting in lithium plating and rapid capacity fading. There are several design strategies that cell designers can employ to counteract this type of behavior. Some of them is like optimizing your electrode structure, but also optimizing the stack pressure and the compression. But on the other hand, there's in terms of separator selections, there's also low swelling separators that can help immensely to reduce this issue. At Celgard, we developed our so-called S-series trilayer that are differentiating from the traditional trilayer by an improved layer structure and also improved pore size. This helps to create an optimized electrolyte reservoir in the middle PE layer, but also helps to with thermal abuse performance due to faster shutdown of our optimized layer structure. Additionally, the low YAR and the higher porosity help to improve the power performance and enable therefore the best rate capabilities among all of our trilayers. Here's an actual example of the swelling in percentage. The separators were immersed in D2 carbonate for 1 hour and we afterwards measured the swelling. So compared to a standard tri-layer, the S series actually shows a lower swelling, but even as high as up to 38% of reduction in swelling. Therefore, we can observe less can deformation, especially after formation in prismatic cells. But additionally, the low swell S series also has a low rebound. This helps to facilitate the can insertion of the jelly roll into the hard case prismatic can. And also same is valid for the cylindrical cans. As earlier mentioned, the improved structure also allows for high power performance due to increased porosity, as you can see in this table, but also decreased internal resistance and decreased air permeability. This makes S-series a unique fit, especially in UPS systems using prismatic or cylindrical cells. So to summarize, we as SAIC are well positioned to serve both the North American market, but also the global battery supply chain. We are offering membrane solution for today's major markets as well as emerging markets. And we have solutions from wet processed polyethylene, our high-pore separators, but also to dry processed polypropylene, our Celgard separators, as well as dynamic separators for our legacy lead acid market. When it comes to the value of Celgard, especially in ESS cells in particular, I would like to highlight 3 areas, which are safety, cost, and performance. So safety always comes first. Our membranes have a proven zero harm record and are already trusted by leading energy storage cell manufacturers worldwide today. On cost, the dry process separators are inherently more cost effective, deliver a lower total cost of ownership, and in large cell manufacturing also help to reduce production cost while boosting the productivity and yield. And finally, not to forget about performance. Celgard membranes enable high capacity retention, which is critical for applications like load leveling, for example, or also extend cycle life and reducing, therefore, the need for replacement and maintenance cost. They support also fast charging and high rate capability, making them ideal for frequency regulation. They also minimize self-discharge and ensure that you have an extended storage life. This is also important in applications such as uninterruptible power supplies. Altogether, this combination of safety, cost, efficiency, and strong performance makes Celgard a powerful solution for your energy storage cell applications. So with that, I would like to conclude my session, and please feel free to reach out to us if you have any questions about high-pore, Celgard, or any of our other product offerings that I presented today. And thank you for your attention. I also want to give a shout out that we have actually at the battery show that is coming up in October, we have a Volta mix and mingle breakfast on the 8th of October from 7:45 a.m. to 8:45 a.m. And we are happy to see you there and welcome you. If you want to participate the mix and mingle breakfast, please make sure to register beforehand. If you need the registration link, you can reach out to us or also to the Volta Foundation. Thank you, everybody.